by induction. It's one of those parts of maths that I personally don't enjoy too much, but we need to know how to do that. Okay, so let's see. Here we have identity that we have to prove by induction for all n values that are natural. So how do we do that? We do that a little bit in step. First thing, we are testing for n equal 1. Now, don't get confused about it. What that means that here, if I keep adding numbers, okay, so 3, and they are saying the next will be 4, 5, all the way to any number we want. But this time we are testing for 1. So we are saying 1 should be equal, instead of n here, 1 multiply, again 1 plus 1 over 2. And then when we put that in the calculator, we get that that is 1. So yes, it is true, we tested it. Then the second part, we're making an assumption. So assume that it is true for n equal, n equal k. Now, basically what I'm doing here, you rewrite that, but instead of n, you put letter k. So everything the same, just replace n with k. So is enough step, isn't it? 3, this is where we prove it's true for next number, that case k plus 1. So again, not to get confused, it is a sum. So let's say that k is 7, that means that will be 8, isn't it? So it will be 7 plus 8. Yeah? So that's what we do here. On the other side, we replace k with k plus 1. So instead of this k, I have k plus 1. Instead of this k, I have k plus 1. And let's not forget there is another one here. That disappear over 2. Okay. Now, here we are using in our proof this assumption. So we are saying this part, that is the same as this part, and this part is the same as this part, therefore I can replace it. Yeah? So next line, we replace it. We are saying k plus 1 over 2 plus, and then the rest k plus 1 equal, and then the other side. Now, there are two ways of solving that. We can go into factorizing mode, but I personally am not, again, fan of factorizing. I just prefer to multiply stuff out. So the idea is that both sides of the equation should be the same, because they are not the same. Looking at it, I cannot say that they equal because they don't look the same. So I'm saying, okay, let's get that on one fraction line. That means common denominator is 2, but that means that this I have to multiply by 2 because originally I had 1 here. Yeah. So let's write it. I'm just going to kind of, don't jump the steps, just write everything out. But when you kind of get good at it, you know you can jump some steps. But here, let's break it down step by step. Okay, so what do we do here? Well, we multiply the bracket here and here. And we're going to be multiplying bracket. Well, actually, let's add up these two before we multiply the bracket so that we don't have that much multiplication. So here we are multiplying the bracket k by k, k to the power of 2. K by 1, that's k. 2 by k, that's just 2 by k. And 2 by 1, that's 2. And then over 2. On the other side, let's just change that k plus 2. Okay, so here I'm saying I can add those two. So I have k to the power of 2, 1 and 2, that's 3 together, plus 2 over 2. And on this side, let's multiply. K by k, that's k to the power of 2. K by 2, that's 2k. 1 by k, that's k. 1 by 2, that's 2. And again here, I'm sure you can see it already, those two can be added. So this side, oh, where did the power of 3 came from? power of 2 plus 3k plus 2 over 2. And then on the other side, k to the power of 2 plus 3k plus 2 over 2. Now we can say they are exactly the same, isn't it? That's the main idea of the proof. So we are saying, therefore, true for n k plus 1, because that's what we were proving, isn't it? But we use an assumption. Here we use this assumption. So we are saying if true for n equal k, isn't it? And then we are going back to what we were proving, isn't it? True for all n. So we are saying, therefore, true for all n that are, sorry, that's, I don't know where is euro sign coming from, belong to n. And then that's our full proof.